So here we are at Caumsett State Park, North Shore of Long Island. As teachers and students, sometimes the goal is like, label the map, label the Atlantic Ocean, label the sound, label where Caumsett is. Look at this. It's a living, breathing place. Just listen to the soothing waves. Think about what body of water is there. Okay, by now you probably figured out it's the Long Island Sound. But we don't want to just be like, that's the Long Island Sound. Think about, how did this estuary come to be? So we hope that this kind of virtual field trip to Long Island Sound and Caumsett has you thinking about stability and change, has you thinking about energy and matter, has you thinking about the major cause and effects of glaciation, and then the ongoing changes of erosion and deposition. It's a beautiful, beautiful spot to just appreciate nature and, of course, to study it.
Today on our field trip, we're going to visit Caumsett State Park, which is located on the north shore of western Long Island. Looking at the digital elevation topography model of Long Island, we can see that Caumsett State Park is located within the hilly North Shore region of glacial moraine, north of the ridge of the Harbor Hill moraine, in this area of Long Island, which is characterized by necks of land separated by deep, narrow valleys that form the harbors. Zooming into Lloyd Neck, we see that Lloyd Neck is an island connected to the mainland of Huntington to the south by a narrow strip of land, a tombolo, which has a causeway that you can take to get out to Lloyd Neck. And then you enter Caumsett State Park, and the state park itself occupies more than half of the Lloyd Neck Island. Entering the park, you can park, and then it's a 2-mile hike to get down to the shoreline at the fishing access, and then you can walk along the shoreline and over to the vicinity of Fresh Pond, and then hike back up the Mansion House. This is the old Marshall Field Estate, one of the Gold Coast estates on the North Shore of Long Island. So you can hike back up to the Mansion House and then walk back to the parking lot. It's about a 5-mile round trip. If we take a look at the topography of Lloyd Neck, what we see is that there's a broad elevated plateau that slopes down to the coastline, a number of low-lying, often marshy areas, and there's one area where the elevated region intersects the coastline, and it's here that the storms coming off of Long Island Sound are eroding into the subsurface and exposing the geology of the North Shore of Long Island. So there are some beautiful cliff exposures along the North Shore here, and that's what we're going to be exploring on our field trip today. If we fly down and take a look at the North Shore, take a look at the coastline of Lloyd Neck, and if we fly in for a closer look, the fishing access puts you out over just on the right side of the image here, and then you walk along the beach and you see these beautiful cliff exposures of the sediments that are underneath the surface along the North Shore here. So we are going to investigate some glacial outwash deposits on the western cliff exposures, and then we'll walk a little bit further east and take a look at some older deposits which have been emplaced above sea level. These are Cretaceous sands and clays. We'll talk about that. And then we'll go a little bit further east along the shoreline where we can see some beautiful examples of glacial till. Okay, so we are at Caumsett State Park, which is one of the premier locations on Long Island to think about and to see the geology that makes up Long Island. The reason Caumsett State Park is such a cool place for geology is because of this beautiful cliff face where the waves from Long Island Sound have eroded into the edge of the North Shore of Long Island, exposing the layers that Long Island is made of.
So here we are at Caumsett with Diana, the ever inquisitive student, and she has some questions for Brett about what she's noticing and how this all got here.
Yes, because I've been told so much about glaciers moving along, and I've never really even understood what a glacier is and how that all happens.
So the way glaciers work is you have a place, usually in the north, in the far north, where it snows more in the wintertime than melts in the summertime. And so every year a little bit more snow piles up, and the snow pile gets thicker and thicker and thicker. And as the snow pile gets thicker, it compresses and the snow transforms to ice. And so you build up this enormous pile of ice.
We're talking millions of years.
Well, thousands of years, right? So every year, over decades, over centuries, over millennia, the snow is piling up because it snows in the wintertime, and then in the summertime it doesn't all melt completely. So every year you add another layer of snow, which compresses to ice, and then the ice piles up. And the thing about ice is that as it gets thicker and thicker and thicker, it starts to flow like a fluid, right? Imagine taking a ice cold pitcher of maple syrup and slowly pouring it out into the middle of a table. The syrup's going to pile up, but the pile of syrup isn't going to get very thick before it starts to flow outward. Right. And that's what glaciers do. So this pile of ice begins to flow outward in all directions away from where it's accumulating, and it will continue to flow outward until it reaches a point where it's melting at the same rate that it's flowing. And when the ice pile kind of flows outward and reaches a point where its edges are melting away at the same rate that new ice is coming in, that's where the glacier comes to an end. That's what we call the terminus of the glacier.
And it disconnects.
Well, so the ice just melts into water, right? Or if the ice reaches the ocean, it breaks up into icebergs, right? So the ice will continue to flow until it reaches the ocean, and then the glacier will stop and just continually break up, producing icebergs. In the case of the last ice age, the center of ice accumulation was way up in Labrador, up in northern Canada, and the ice flowed radially outward till it reached the ocean to the east, but to the south it continued to flow until it reached the vicinity of Long Island. And at the point where the edge of the glacier was where Long Island is, it was melting fast enough that as new ice came in, the ice just melted away, so it couldn't really move any further. And glaciers, when they reach that point, they're in a sort of what we call a dynamic equilibrium, where, okay, new ice is flowing in as the old ice is melting away. If you increase the rate at which the ice is flowing, the glacier will advance a little bit farther south until the melting rate catches up. If you increase the temperature and make the ice melt faster, the glacier will move back because it will melt faster than it's flowing, and it'll retreat until it reaches a point where it's balanced again. So that's what happened in the vicinity of Long Island about 20,000 years ago. You had the ice from the edge of the glacier reach this point, and then for a period of several thousand years, it was pretty much in equilibrium here. Maybe advancing a little bit farther when the rate of ice flow increased or the temperature cooled down, and then if the temperature warmed up a little bit, retreating a little bit. And so the ice front kind of shifted back and forth around 20,000 years ago for a few thousand years until things started to warm up permanently, and then the ice began to melt back, first up into Connecticut and then across New York State and then back up into Canada. And by about 10,000 years ago, the glacier had melted away completely.
And what you're left with is everything that the glacier had collected along the way.
Right, exactly. So a glacier that's flowing to a point and then melting away is like a conveyor belt. So this enormous pile of ice, which is very, very heavy, is grinding and scraping along the surface, plucking up pieces of bedrock, boulders, scooping up soil, sand, gravel, and picking all that up into the ice. And then it moves along with the ice, but when the ice melts, the rock and debris in the ice doesn't melt, it just gets dumped.
So we're standing on what was inside the glacier.
Right, exactly. We are standing on this enormous pile of sand and mud and cobbles and boulders that was carried by the ice and then dumped here when the ice melted. Does that make sense?
Yes.
Oh,
Well, more sense than it ever has.
Look at the beautiful landscape of the cliffs of Caumsett State Park. You probably have lots of noticings and lots of wonderings about how that cliff got there, about what natural processes are changing it over time. So you've noticed this beautiful cliff with its horizontal layers. You've been asked, is it wind or water deposition that is the primary agent that caused it? We'd like you to form a line of reasoning that makes sense to explain whether wind or water deposition is the primary cause.
okay. So what we can see in the cliff face here is a bunch of layers. And if you look carefully, you'll notice that the layers kind of in the top half of the cliff face have lots and lots of cobbles and pebbles. So it's pebbles and cobbles and sand. And these are layers of what we call glacial outwash. So this is sediment that was melted out of the glacier and then carried and deposited by running water. How do we know it was deposited by running water? Well, we know because it's layered, right? So if you want pebbles and sands to be strewn out in discrete layers, you need a fluid to carry them and deposit them. And that fluid could be water or it could be air, but we know it's not air because the pebbles and cobbles are too big to be carried by the wind. Wind can only carry very fine particles. So the fact that we have coarse particles strewn out into layers tells us that these particles were deposited by water. This is the melt water that was flowing off of the ice. So as the ice melted and released all of the rocky material that it was carrying, the melt water flowing away from the ice picked up that material and laid it out into layers. You can also deposit sediments from ice, just directly melting them out of the ice, but if you do that, you will get a material that is not layered, that is just a jumble of cobbles and pebbles and sand and silt and mud, and we call that material glacial till, and we'll see an example of glacial till further down the beach in the cliff. But here, what you see is layered material, glacial outwash, and then about halfway down the cliff, you don't see the layering quite so well anymore. The material changes. It's still layered, but it's mostly sand. And it turns out that the material in the lower part of the cliff is not glacial. This is the older layered material that makes up the basement under Long Island, under the glacial material, below sea level. And that sediment dates back to the end of the age of dinosaurs, about 70 million years ago. So we have the older material that forms the foundation that Long Island is basically sitting on, exposed in the cliff with the younger glacial material deposited on top. Now, the material below, the sandy layers below, that's called the Raritan Formation. And the Raritan Formation is an extensive deposit of sand that was brought to the eastern edge of North America by rivers about 70 million years ago. And the Raritan Formation extends all the way down, it's under Long Island, where it forms part of the aquifer system, and then it continues down the coast of New Jersey and down into Maryland. How did this older material, which is mostly below sea level everywhere else, end up in the cliff face above sea level here? So what we're looking at here is a section along the cliff face where a large block of the older material that's beneath Long Island got bulldozed by the ice as it advanced to the south and pushed up above sea level, and then as the ice melted, when the glacier retreated, the outwash was deposited on top. And we have reason to believe that not just the older material below was pushed by the ice, but in fact the glacial outwash was also pushed by the ice. all of this material was deposited a little bit further north in front of the ice, and then as the ice advanced, it was pushed along and bulldozed into its present position where we see it being exposed along the cliff wall.
Here at Caumsett, on this beautiful day with Gail, Brett, and Diana, we're walking along and we notice something else. How did these get here? The whole time we've been walking, there's been trees up at the rim, but now we notice suddenly there's a clump of trees here. So the question I have is, how did all that soil get here? And I'm wondering, did the trees come down with the soil? Or did the soil get dumped and then the trees grow? What's your reasoning? What evidence can you gather to try to explain this clump of trees right here along the shore? So Gail, you're here. Share your line of reasoning. What do you think?
Okay, so we noticed this clump of trees. We noticed somehow this soil here must have been up there at one time. But what came first, the soil or the trees? Or did they come together? Well, now that I look around the back, I take a peek, and I look up at the top of the ridge, I notice the same type of trees, and they're the same size. So, that makes me think that the trees moved with the soil that came down together because they were part of that group of trees up there.
Sounds logical. So the more I stood with Brett and we were having a lovely conversation about glaciation and the formation of these beautiful cliffs, I stood here, and it's important to look and then look again. So what jumped at me at first was listen. Whoa, look what's going on. We got another cause and effect. Seemed like all of a sudden we had a little mini pebble rock avalanche. So it's important to look and then look again. So what jumped out at first were the beautiful horizontal pattern of layering. Then I looked again and I noticed something else. Keep looking. See if you notice another, I don't know what to call it. Brett, what would you call it?
Channels.
Channels. See if you notice those. What do you think caused them? So we're taking you on a little bit of a walk. Join us. Put yourself right here with us. What are you noticing? Oh my goodness. Pretty dominant here. What do you notice about the pattern of the channels? What do you think caused them? What do you think the effect of the channels are in the overall landscape? Then if you keep noticing, you see this tree. Wonder what happened there. It'd be kind of fun to write a story in our imaginations, our scientific minds, thinking about how it used to be, how it is now, what the future. We're doing our lovely walk from west to east along the beach at Caumsett, and all of a sudden I noticed this. It's hard not to. What do you notice about this beautiful rock? And then look around. What do you notice? Lots of boulders scattered along the shore here. There's got to be a reason. What do you think it might be?
There's a general rule about glacial erratics. The larger the boulder and the more angular the boulder, the less distance it traveled in the ice. So a really big boulder like this one, really big erratic like this one, probably didn't come very far from where it began. So this particular erratic was probably plucked from the bedrock beneath Long Island Sound, maybe just a few miles from here, carried in the ice and then melted out, incorporated into glacial till. And as the shoreline of Long Island has stepped back from erosion, this boulder was liberated from the deposits it was in and left sitting here on the beach.
So here we are at another gorgeous point of interest. You might think we went somewhere else, but we didn't. We just kept walking, bringing you along on our stroll along the beach as we headed east. And my goodness, look what we have here. You've got to have a lot of noticings and wonderings. Look at the patterns, look at the colors, look at the texture. I know you can't feel it, but you can almost feel it by looking really closely. Wow. What is similar to this, to what we've already seen? What is different? Quite stunning.
Okay, so we've come a little bit further east down the cliff face, and you probably noticed that it looks quite a bit different from what we've seen before. You have this reddish white material. You can see that it's layered, and it extends quite a ways up to the top of the cliff. We've lost the pebbly, sandy layered material, the glacial outwash. We don't see it anymore. What we're looking at here is the older material that was forming the bottom half of the cliff further west now is the dominant material in the cliff. And you can tell that this material has different properties in the glacial outwash because you can see some holes, some cliff swallow nests way down into the material. You don't see cliff swallow nests in the glacial outwash. It's too crumbly. This material holds together a little bit better. It's very sandy, but it's also got a component of clay which helps it stick together. So this is the Raritan Formation. This is the older Cretaceous age, late dinosaur age deposits that form the basement, or the older material that forms the subsurface on which most of Long Island is sitting and is part of the aquifer system. Again, what we're looking at here is a block of this coastal plain, older coastal plain sediment that got bulldozed up by the advance of the glacier and mixed in with the glacial outwash and glacial till that melted out of the ice. And there are blocks of Cretaceous material. There are blocks of this coastal plain material all up and down the north shore of western Long Island. So at Garvey's Point, you can see the same material. You see it here at Caumsett. Further east, you can see it at Mackinac Indian Hills in the Northport area. Right. So as the ice came down from the north across Long Island Sound, it bulldozed up the material that was already there, the older material that had been deposited, and incorporated it into the glacial deposits that form Long Island.
Do you notice the two lines of seaweed and shells? They're called rack lines. W-R-A-C-K. What do you think those rack lines have to do with the ocean tides? What is the connection between energy and matter at the beach? So here we are with Gail and Brett at Caumsett, and they are curious about so many things, but these particular rocks really grab their interest. So let's zoom in on this one that Gail has. We're not going to tell you what it is. Think about it.
And
you turn it over, Gail?
Flakes.
Oh,
It's breaking down. I think what we call that.
Brett, what grabbed your eyes? These two?
Yeah.
So why don't you guys make some noticings and some wonderings about these rocks?
Well, I noticed the flaky, shiny, glittery crystals that make up this rock, but also I noticed smaller versions of shiny, glittery crystals in this rock. I also noticed that there seems to be some layering, that there's kind of a directionality to the crystals, kind of back and forth across the specimen.
Yep. Notice some layering in this rock. You can see there's alternating light and dark bands. Even though the rock has been a bit weathered. You can also see some shiny crystals, as Brett showed us in the other rock, which makes me think that these two rocks are somehow related to each other or classified together. Okay, so this would be a metamorphic rock, and what happens is when you take a rock and it undergoes a lot of heat and pressure, the crystals recrystallize and form layers, and the layers are compressed. We see it alternates by dark and light, so the different dense materials will be the darker ones, less dense will be the lighter ones. And we also see, once again, some pieces of mica, little flakes of mica, which are very predominant in metamorphic rocks. And I'm looking down at the rocks right now, and just about every rock I see that I pick up is quartz. Quartz is silicon dioxide, and it's very stable in our surface, so this isn't going to degrade or break down to anything else. It's just going to get rounder, and think about why it's getting rounder. We'll come back to that later. But I found this interesting rock, and notice when I touch it, it's becoming powdery. Well, this is a piece of feldspar that is not stable on our surface, so what happens is, over thousands of years, it will break down into these flakes. And these flakes are very small sediments turned into clay. So when we go into the cliffs and we find areas of clay, we know that at one time was a piece of feldspar. And feldspar is part of granite, so if you look at this side of the rock, anything that's not feldspar is going to turn into small pieces, such as quartz crystals, and that's going to be around forever, but not so much for the feldspar.
So this is a piece of hematite, which forms in the glacial sediments, probably from oxygen in groundwater reacting with iron in the sediments. And these very large masses will form that are hollow inside, and people call them Indian paint pots. You can prove to yourself that this is made of hematite. For one thing, it's very, very heavy. That's the iron in the iron oxide. But if we scratch it up, you see that it makes a bright red ochre, and that's the paint that you get from the Indian paint pot. This is a piece of hematite cemented sandstone, probably from the Raritan Formation, which is Upper Cretaceous in age. And slabs of this sandstone are commonly found along the beach. And if you look carefully, you can find fossils of plants. So in this piece here, we zoom in, there's a little fragment of wood preserved on a layer of the sand. Quite a ways east along the cliff face. And what we're looking at here is the uppermost layer from way down at the west end, which has gotten a little bit thicker along the shoreline and dropped down to beach level, so we can see what it's made out of. And if you look, what you notice is material which is very tightly packed. It's not very well layered. You don't see discrete layers, and you see a wide range of particle sizes. You've got boulders, cobbles, pebbles, sand, silt, clay. It's all mixed together, all these different size particles all jumbled together. So this is glacial till, what glaciologists call an ice contact deposit. This is what you get if the ice melts and sublimates away and running water doesn't wash the sediments anywhere. The sediments contained within the glacier are just kind of left sitting on the landscape. And in fact, this particular layer of till was probably melted out of the bottom of the glacier and compacted by the weight of the overlying glacial ice. So this is what you would refer to as a ground moraine. So deposits of glacial till are called glacial moraines, and you also get a kind of a widespread horizontal till beneath the ice that's referred to as a ground moraine. And then above the glacial till, you see the material changes, and it's very well rooted. You don't see a lot of plant roots in the glacial till. It's a little too deep, and it's also a little too difficult to penetrate. It's very, very tightly put together, tightly compacted. But the upper material is more finer grained looking, and it's very loose. And this is a layer of wind-blown glacial material called loess. And loess is very, very finely ground up rock flour, pulverized underneath the glacier. And then once the ice melts away, the wind is able to pick up this very, very fine material when it dries out and blow it some distance. So towards the end of the last ice age, after the glacier had retreated so that the ice was to the north in Connecticut, the Long Island Sound Valley would have been this very, very large, barren, dry valley covered with glacial deposits. The winds coming off of the glacier, so glacier is very cold, the air above the ice is dense and cold, and it descends, and you get blowing off the front of the glacier winds, which are called adiabatic winds. And these winds would have blown south towards Long Island, picking up all of this fine glacial material, carrying it along, and then when the winds hit the hills, the moraine along the north shore of Long Island, they would have slowed down and deposited this material as a layer of glacial loess, which covers much of Long Island. And it's very, very fertile because you have these pulverized fragments of rock, a lot of mineral material, basically unchemically weathered mineral material, makes for a nice fertile soil. So the plants are very happy putting roots down in the loess.
Wow.